We want to determine if each sequence converges or diverges. If it converges, determine what it converges to. To do this, we'll treat the formula for the terms of the sequence as a function of n and determine the limit as n approaches infinity. If the limit equals L, some particular value, then the sequence converges and it converges to the value of L. If the limit does not exist, the limit diverges. For the first example, we have a sub n equals the nth root of 2 raised to the power of the sum of 5 and 4n. We first want to change the form of this formula before we determine the limit. Taking the nth root is the same as raising to the 1 divided by n power. Let's write a sub n as 2 to the power of the sum of 5 and 4n raised to the power of 1 divided by n. From here, we'll apply the power to power property of exponents. Recall when we have a to the power of m to the power of n, we multiply the exponents and get a to the power of m times n. This indicates we can write a sub n as a sub n equals 2 to the power of the product of 1 divided by n and the sum of 5 and 4n. And now let's go ahead and multiply the exponents and write this as 2 to the power of the sum of 5 divided by n and 4n divided by n. Notice in this form we can simplify. 4n divided by n simplifies because n divided by n simplifies to 1. We now have a simpler formula that we can use to determine the limit. We have a sub n equals 2 raised to the power of the sum of 5 divided by n and 4. So now we'll determine the limit as n approaches infinity of a sub n. And now we need to focus only on the 5 divided by n. We know as n approaches infinity, the fraction of 5 divided by n gets smaller and smaller and approaches 0, which indicates the overall limit will be approaching the value of 2 raised to the power of the sum of 0 and 4, which is simply 2 to the 4th, which equals 16. So because the limit equals 16, the sequence converges, and the sequence converges to 16. Let's take a look at this graphically. To take a look at a sequence graphically, we can look at points on the coordinate plane in the form of n, comma, a sub n. Notice here I've entered the exponent of 1 divided by n rather than the nth root. And now we'll look at the first 50 terms. The y values of the points are the terms in the sequence, and it does appear as if they are converging to a particular value. It's a little hard to tell what value that is from the scaling on the y-axis, but if we graph y equals 16, we can see the terms of the sequence are converging to 16. Let's look at the second example. We have a sub n equals cosine of 7 divided by n. Let's go ahead and take the limit of a sub n. Let's first focus on 7 divided by n as n approaches infinity. Again, the denominator is increasing without bound, and because the numerator stays at 7, the fractions get smaller and smaller and approach 0. The limit doesn't approach 0, but 7 divided by n approaches 0. The limit actually approaches cosine 0, and cosine 0 we should recognize is equal to 1. Because the limit equals 1, the sequence converges and converges to 1. And once again, let's look at this graphically. We'll now graph the first 50 points in the form of n, comma, cosine of 7 divided by n, and look at the behavior of the points. Notice the y values, which are the values of the terms in the sequence, are approaching positive 1, verifying the sequence converges and converges to 1. I hope you found this helpful.